All right, so in the last lesson, we saw how we can fit a simple linear regression model. And we saw that an SLR, simple linear regression model, is simply fitting the best fit line to our data, right? So it's building on top of correlation to illustrate that linear relationship with a best fit line. And this line can be defined by this equation here, where y, or y hat, which is the estimated value of y, equals the intercept, beta naught, plus beta 1, which is the predictor variable coefficient times the value of the predictor variable, right? And that gives us this linear line. So we saw when we actually do this with an R, we can get our model output, and we see that in this case we have our predictor variable right here, and we have our intercept, right? So the estimated coefficient for our intercept is 15,938, that is beta naught. And the estimated coefficient for our predictor variable is 110. So 110 is equivalent to beta 1. And we could use that where if we had a house that had 2,000 square feet, we would take 15,938 plus 110 times 2,000 square feet. And that would give us our predicted value of the sale price, which would be right on this blue line. All right. However, single predictor variable models are quite rare. We almost always have more information we can use. So lots of times we want to add additional predictors or predictor variables in our model. And we can do that. And when we do that, let's say we add a single additional predictor, now our equation simply becomes this, where we have what we saw before, y hat equals beta naught, our intercept, plus the coefficient for our first predictor variable. And then we're going to add the second part here, which is adding a second coefficient for our second predictor variable. Okay. And when we do this within R, we have the exact same code that we had before, except within our fit here, you're going to see sale price is now a function of our ground living area plus our year built. And when we run that, now we see an additional line in our model output that provides year built and the coefficient. Okay, so now we have our intercept, which has changed from before because we're using more information. So all our estimates get changed. We have a new intercept estimate. We have the coefficient for ground living area and the coefficient for year built. Now, what is actually happening here is now we've gone away from fitting a single line to now fitting a plane, right? And so we can see that in this image here, where we have all our individual homes are these points in the scatter plot. We have sale price on our vertical axis here, and then we have year built along this axis and ground living area along this, right? So now we can kind of move this around and we can see that we actually have a three-dimensional plane here. And that is our estimate. That is what this equation is actually giving us, right? So we could actually move along this plane and we get different sale price predictions based off of the value for the year the home was built and also the square footage of that home. So does this model actually improve performance? Well, we can go ahead and follow the same pattern we did before, where we compute the RMSE of our single predictor model, which we see we had $55,942 was our RMSE. Where if we take model 2, which is the multiple predictor model that we just created, our RMSE on our test data moves down to 45,736. So what this means is that by adding an additional predictor variable, that we were able to reduce the RMSE on unseen data, when we make predictions on unseen data, by close to $10,000. This means the average prediction error of our model is actually decreased by roughly 10,000, which is a great thing.